Hello everyone. Previous lecture we have studied how to define the inverse trigonometric function, then how to define the domain and range for the given inverse trigonometric functions. Now in today's lecture we will study the properties of inverse trigonometric functions. We have to define the properties of inverse trigonometric function. Okay, so we go with our first property here, property number first. In that we consider three sub cases. Okay, here in first we consider here sine inverse of x is equal to here cosec inverse of 1 upon x. Okay, and here this x belonging to close interval minus 1 to 1, and here x is not equal to 0. Now here remember, to define the properties we consider the principal value branch of the given inverse trigonometric functions. And by using this principal value branch, here I write the sine inverse of x is equal to cosec inverse of 1 upon x, and here value for x belonging to close interval minus 1 to 1. Okay, so remember this property. Let's go with our second property. Here cos inverse of x is equal to here sec inverse of 1 upon x. Here again we define this property by using the principal value branch of the given inverse trigonometric function, and here value of x belonging to close interval minus 1 to 1, and here again value of x is not equal to 0. Okay, next here for tan inverse, here in third we consider tan inverse of x, and this is equal to here tan inverse of x is cot inverse of 1 upon x, and here x is greater than 0, strictly greater than 0. So this is our first property and very important property. Let's go with our second property. Okay, in that we consider sine inverse of, in first we consider sine inverse of minus x. Here sine inverse of minus x is always minus sine inverse of x. Remember this. And here a value of x belonging to close interval minus 1 to 1. Then we go with our second sub point. Here we consider tan inverse of minus x. Tan inverse of minus x is again minus tan inverse of x. Again by using the principal value branch, here we define this property, and here x belonging to r, that is x belongs to r. Next here in third we consider cosec inverse of minus x is equal to, this is again is a minus cosec inverse of x, and here a value of x, that is mod of x is greater than equal to 1, that is value of x is less than minus 1, or here x is greater than 1. That is by using the principal value branch we define this property. Okay, then we go with our third property. Let's go with third one. Here given cos inverse of minus x. Cos inverse of minus x. Here cos inverse of minus x is always here pi minus cos inverse of x, and here this x belonging to close interval minus 1 to 1. Okay, this is our first sub point. Then in second we consider cot inverse of minus x, and this cot inverse of minus x is again here pi minus cot inverse of x, and here value of x belonging to r. Then in third point, we consider sec inverse of minus x, okay, and this is equal to here pi minus sec inverse of x. Again, here value of x, that is here mod of x is greater than equal to 1, that is value of x is less than minus 1, okay, or we consider x is value of x, that is 1 is greater than x. Okay, then so we define this third property again by using the principal value branch of the given inverse trigonometric functions. Okay, let's go with fourth property. Here given in first sine inverse of x plus cos inverse of x. Remember, here given sine inverse of x plus cos inverse of x, and this is equal to pi by 2. This is equal to pi by 2. That is addition of sine inverse of x and cos inverse of x is always pi by 2, and here x belonging to closed interval minus 1 to 1. Second, here in second we consider tan inverse of x plus cot inverse of x, that is addition of these two inverse trigonometric functions is again pi by 2. Okay, here value of x is belonging to r. Then here third subpoint, here in third we consider sec inverse of x plus cosec inverse of x, and this is equal to again addition of these two inverse trigonometric functions is pi by 2. Again here mod x is greater than equal to 1. Value of x is here greater than equal to 1. Mod x is given. So we consider here x is greater than equal to 1 or value of x is less than equal to minus 1. Remember this. So we see this fourth property. Let's go with our fifth property. Here in fifth and here in first subpoint we consider tan inverse of x plus tan inverse of y. Okay, and this is equal to, now here remember addition of tan inverse of x and tan inverse of y is given, and if here product of x and y, I repeat again, if here product of x and y is less than 1, if product is less than 1, then here we define tan inverse of, here we define tan inverse of x plus y, this divided by here 1 minus xy. Here inside this bracket, here I repeat right again, tan inverse of x plus y, this divided by 1 minus xy. And here condition is, here product in between x and y is less than 1. If product is less than 1, then we use the same property. Okay, then here in second point, again we consider addition of tan inverse of x and tan inverse of y. Okay, here if product of x and y, that is product in between x and y is greater than 1, then we define here pi minus tan inverse of, inside the bracket, x plus y upon 1 minus xy. And here remember condition is, here product of x and y is greater than 1. Here this product is greater than 1. Okay, and here in third point, we consider subtraction in between tan inverse of x and tan inverse of y. Okay, and this is equal to here tan inverse of inside the bracket. Okay, here in numerator x minus y. Now here remember, if in between the two inverse trigonometric function, if minus sign is given, then in property, then in the formula and in numerator we use minus sign. If addition is given, then in numerator we use plus sign, and in denominator we consider opposite sign of the given. That is, if your plus is given, then in denominator we consider minus sign. Similarly, here in the next property, if minus sign is given, then in numerator we use minus sign, and in denominator we consider plus sign. So in denominator we have 1 plus xy. Okay, so again we define this fifth property by using the principal value branch of given inverse trigonometric functions. Okay, so now we go with our sixth property. Here in sixth, given tan inverse of, here I write 2 into tan inverse of x. 2 into tan inverse of x. Okay, so here I write in the form of trigonometric function sine inverse. Firstly, we define property, and in that property we consider trigonometric function sine inverse. Okay, so here sine inverse of 2x upon 1 plus x square. I repeat again, 2 into tan inverse of x is equal to sine inverse of 2x upon 1 plus x square. Then in second, here 2 into tan inverse of x is equal to, now we have to define this property by using trigonometric function cos inverse. So here cos inverse inside the bracket we consider 1 minus x square upon 1 plus x square, and in third point we consider 2 into tan inverse of x. Again, in this property we have to consider the inverse trigonometric function tan, that is tan inverse. Okay, so here tan inverse inside the bracket, here 2x upon 1 minus x square. So in total we have 6 properties related with the inverse trigonometric functions, and these all properties are defined by using the principal value branch of the given inverse trigonometric functions. So remember these all properties. Now in this lecture we are going to study some examples. We are going to see some examples related with these properties. Okay, so we go with examples through the following. First is, in first we consider tan inverse of 1 upon 2, tan inverse of 1 upon 2 plus tan inverse of 1 upon 3. 1 upon 3 is equal to pi by 4. Is equal to pi by 4. Okay, we have to prove this. Here we consider LHS first. By using the LHS we find RHS. Okay, consider LHS first. Consider LHS. Here in LHS, given tan inverse of 1 upon 2 plus tan inverse of 1 upon 3. Now everyone knows here this tan inverse of 1 upon 2 plus tan inverse of 1 upon 3 is in the form tan inverse of here x plus tan inverse of y. And we know the property related with this form. And is tan inverse of x plus tan inverse of y. And to define the property, before considering the property, here we consider product in between x and y. Here x is 1 upon 2, y is 1 upon 3. So x into y is equal to 1 upon 2 into 1 upon 3. And we know this is 1 upon 6. And here 1 upon 6 is less than 1. So we consider our property number 5. In that first, here tan inverse of x plus tan inverse of y is equal to tan inverse of x plus y upon 1 minus xy, and condition for this is here x and y, product in between x and y is less than 1. If product is less than 1, then we use this property. Here again in this example, product is less than 1. Okay, so we use this fifth number, property number 5th. So this is equal to here tan inverse of, inside the bracket we consider x plus y, means 1 upon 2 plus 1 upon 3, this divided by 1 minus xy, means 1 minus 1 upon 2 into 1 upon 3. Okay, now this is equal to here tan inverse of, inside the bracket and in numerator we know here 1 upon 2 plus 1 upon 3 is 5 upon 6. Okay, then in denominator here given 1 minus 1 upon 2 into 1 upon 3. We know here 1 minus 1 upon 6 is given, and we know 1 minus 1 upon 6 is again is 5 upon 6. Okay, so in next step, here this is equal to tan inverse of, we know 5 upon 6, 5 by 6 upon 5 by 6 is 1, and we know tan inverse of 1 is pi by 4. That is, value of tan pi by 4 is always 1. So tan inverse of 1 is pi by 4, and this is our RHS. So we prove here tan inverse of 1 upon 2 plus tan inverse of 1 upon 3 and is equal to pi by 4. Okay, so very simple example it is. By using our property of inverse trigonometric function, we find this relation. Okay, let's go with our next example. Example number 2. Here given 2 into tan inverse of 1 upon 3. 2 into tan inverse of 1 upon 3 is equal to given tan inverse of 3 by 4. Tan inverse of 3 by 4. Okay. Again, by using our property, we have to show this LHS is equal to RHS. Let us consider LHS. Consider here LHS is equal to 2 into tan inverse of 1 upon 3. Now here we know this is in the form here 2 into tan inverse of x. 2 into tan inverse of x. And we know property related with this 2 into tan inverse of x. Okay. Now here in RHS given tan inverse of 3 by 4. That is in the form of tan inverse is given. And we know our property number 6, and in that our third point, here I repeat property, we know tan inverse of x is equal to, here tan inverse of, inside the bracket, 2x upon 1 minus x square. We see this in property number 6. So we use same property in this example. Okay, so here I write this as tan inverse of, inside the bracket, 2 into x. Here x is 1 upon 3. Then this divided by 1 minus x square means 1 upon 3 this bracket square. Okay, remember this property. This is equal to, here tan inverse of, inside the bracket. Here 2 into 1 upon 3 is 2 upon 3. This divided by, in denominator, here 1 minus. We know 1 upon 3 square is 1 upon 9. Okay. Then this is equal to, here tan inverse of, inside this bracket. Again in numerator we consider 2 upon 3. Then in denominator we know 1 minus 1 upon 9. We know 1 minus 1 upon 9 is, here 8 by 9. Here is 8 by 9. Okay. Then in next step, this is equal to tan inverse of, inside this bracket. Here given 2 upon 3, this divided by 8 by 9. Okay, here I write this as 2 upon 3 into, in denominator given 8 by 9. So I write here 9 by 8. Here I write 9 by 8. This is equal to, here tan inverse of, inside this bracket, we get 3 upon 4. And this is our RHS. This is our RHS. So we prove here the relation, that is the 2 into tan inverse of 1 upon 3, and this is equal to tan inverse of 3 by 4. So by using our property of inverse trigonometric function, we prove this second example. Now we go with our third example. We go with third one. In third, given cos inverse of 3 by 5, cos inverse of 3 by 5 plus cos inverse of 4 by 5, this is equal to pi by 2. This is equal to pi by 2. Again, by using our property, we have to prove this LHS is equal to RHS. Okay, let us consider LHS first. Consider LHS. Here in LHS given cos inverse of 3 by 5 plus cos inverse of 4 by 5. Now we know here one property. Let's remind our one property. Here everyone knows sine inverse of x plus cos inverse of x, and this is equal to pi by 2. We know this property. We know this property. I repeat again. Here we know sine inverse of x plus cos inverse of x is equal to pi by 2. And by using the same property, we find this pi by 2. We find this pi by 2. Okay. So here we have to make one change. We have to convert this cos inverse of 3 by 5. Okay. This cos inverse to 3 by 5 into sine inverse of x in the form of sine inverse. Okay. So we consider the first case. Let us consider this as 1. Okay. Here we consider cos inverse of 3 by 5 as x first. Let here cos inverse of 3 by 5 is equal to x. Okay. Then by using our definition of inverse trigonometric function, here I write this as cos x is equal to 3 by 5. Cos x is equal to 3 by 5. Okay. Here we know x lies in between 0 and pi by 2. We know this. Okay. So here sin x is sin x is greater than 0, that is sin x is positive. Let's find sin x by using our first fundamental identity. Okay, we know our first fundamental identity is here sin square x plus cos square x is equal to 1. We have to find sin x, so I write sin square x separately. Here sin square x is 1 minus cos square x. Okay, now taking square root on both the sides, here we get sin x is equal to, inside the square root, 1 minus cos square x. Now here we know cos x is 3 upon 5. Okay, so I write this as, inside the square root, 1 minus 3 by 5, this bracket square. Now this is equal to, here inside the square root, 1 minus, we know 3 upon 5 square is 9 upon 25. This is equal to, here inside the square root, we know 1 minus 9 by 25 is here 16 upon 25. And we know here square root of 16 upon 25 is 4 upon 5. We consider positive value since sin x is positive. Okay, so here sin x is equal to 4 upon 5. So we replace our cos inverse of 3 by 5 by using here sin x, that is, or I write here one step. Here if sin x is equal to 4 by 5 is given, then here x is equal to sin inverse of 4 by 5. This is by using our definition of inverse trigonometric function. Now we replace this x, that is cos inverse of 3 by 5, by using sin inverse of 4 by 5 in 1. Okay, so from 1 here LHS is equal to, okay, here we replace cos inverse of 3 by 5 by using sin inverse of 4 by 5 plus, in next cos inverse of 4 by 5 is given. Okay, now here in both 4 upon 5 is given. If these two are same, then we use our property. We know sin inverse of x plus cos inverse of x is pi by 2. So here also we get pi by 2. And this is our RHS. This is our RHS. So by using our property, here we prove cos inverse of 3 upon 5 plus cos inverse of here 4 upon 5, and this is equal to pi by 2. This is equal to pi by 2. Okay, so very simple example it is. Now we go with our next example. Okay, here given sin inverse of 3 by 5, sin inverse of 3 by 5 plus cos inverse of 12 by 13, 12 by 13, this is equal to sin inverse of 56 upon 65. Sin inverse of 56 upon 65. So by using our definition of inverse trigonometric function and properties, we have to prove this relation. Okay, so to prove this, we consider this sin inverse of 3 by 5 as x first, then cos inverse of 12 by 13 as y, then here sin inverse of 56 by 65 as z. Okay, so we go with first, let here sin inverse of 3 by 5 is equal to x. By using the definition of inverse trigonometric function, here I write sin x is equal to 3 upon 5. Here we know x lies in between 0 and pi by 2. So here sin x is positive. Sin x is greater than 0. Okay. Here sin x is greater than 0. Then cos x is also greater than 0. Okay. So here we find cos x. Here we find cos x. So by using our first fundamental identity, here cos x is inside the square root 1 minus sine square x is equal to, here inside the square root 1 minus, we know sin x is 3 upon 5, so its square is 9 upon 25. Then in next step we consider here cos x is equal to, inside the square root, here 1 minus 9 by 25 is 16 upon 25. Okay, then we know the 16, square root of 16 upon 25 is 4 by 5. We consider the positive value. Okay, so we get here cos x is equal to 4 by 5. Now in second we consider cos inverse of 12 by 13 as y. Let cos inverse of 12 by 13 is equal to y. Okay, then by using definition, here I write cos y is equal to 12 by 13. Here y is lies in between 0 and pi by 2. Okay, therefore here sin y is greater than 0. Let's find sin y by using our first fundamental identity. Okay, here sin square or sin y is equal to, inside the square root 1 minus cos square y. Okay, now this is equal to, here inside the square root 1 minus, we know cos y is 12 by 13 and we know 12 by 13 square is what? 144 upon 169 is 144 upon 169. Okay, then in next step, here I write sin y as equal to, inside the square root, we know 1 minus 144 upon 169 and is here 25 upon 169, and we know square root of 25 upon 169 is 5 upon 13. We consider positive values in sin y is greater than 0. Now we consider this sine inverse of 56 upon 65. Now consider sine inverse of 56 upon 65, okay, is equal to z. Then by using definition, here we get sin z is equal to 56 upon 65. Okay, now here we have to prove, here x plus y is equal to z. We know this sine inverse of 3 by 5 is x. We know this cos inverse of 12 by 13 is y. Then we know here sine inverse of 56 upon 65 is z. So here we have to prove, x plus y is equal to z. And to prove this, we consider sine of x plus y. We consider sine of x plus y. And here we know sine of x plus y is sine x cos y plus cos x into sine y. We know this. This is equal to, here we know sine x is, here sine x is 3 upon 5. Okay, so we replace sine x by using 3 by 5 into here cos y, we know here cos y is 12 by 13. We replace cos y by using 12 by 13 plus, in next we know cos x, here cos x is 4 upon 5. Okay, so we replace cos x by using 4 upon 5 into, then sin y, we know sin y is 5 by 13. Now this is equal to, here we get, we know 3 into 12 is, 3 into 12 is 36, this divided by 5 into 13 is 65 plus 4 into 5 is 20, this divided by 65. Okay, and in last, here we get sine inverse of, okay, sine of x plus y is equal to, we know 36 plus 20 is 56. So 56 by 65. Therefore, here I write sine of x plus y is equal to, we know this 56 upon 65 is sine z. Okay, so we replace this by using sine z. Now by comparing both the sides, here we get x plus y is equal to z. X plus y is equal to z, and this is we have to prove. That is, here we prove, here x, we know x is sine inverse of 3 by 5. Okay, so we replace x by using sine inverse of 3 by 5 plus, we know y, here y is cos inverse of 12 by 13. Okay, we replace y by using cos inverse of 12 by 13. This is equal to z. We know z is sine inverse of 56 by 65. Sine inverse of 56 upon 65. Okay, so by using our definition of inverse trigonometric functions, okay, and by using the property, here we prove this relation. So very simple example it is. So in today's lecture, we see the concept for properties of inverse trigonometric functions, and we see some important examples related with these properties. Okay, so we stop here. Thank you.